Okay, hopefully I just convinced you that this partial answer is true. So that this kind of crazy operation of Hadamard transform, which really just means do average and deviation to every qubit, which you can see does something kind of weird. Like, I mean, it mixes up, like you get some combination of averages and deviations going into like different locations in the cube. And we're going to figure that all out next time. But like the thing we just figured out is like, okay, if you just concentrate on what happens, what you get to in the all zero string, it has a very clear meaning. It's the average of all the original amplitudes. So let me ask you a follow-up question about what happens when we do this in the middle of this paradigm where we're we have some Boolean function we have the code for, we load its whole truth table in plus or minus 1 notation into the state, and then we do average and deviation on everything. So question. Suppose we do this thing. Suppose we load the plus or minus 1 notation truth table of some function f with n input bits and 1 output bit into our state, and then do this Hadamard transform. My question is, this is a question for you. What does it mean in human terms if the resulting amplitude on all zeros is itself 0? In other words, what does it mean if like an amazing cancellation happens and the final amplitude here is literally exactly 0? It all cancels out. When does that happen? Yeah? Exactly. So the answer is, well, all these entries are plus or minus 1. The way that they could cancel out to 0 if you take the average has to be like perfectly balanced, right? It has to have an equal number of plus or minus 1s. And that's in plus or minus 1 notation. You might say in 0, 1 notation, it just means there's like an equal number of zeros and ones in the truth table of f. I'm going to say it like this. The truth table of f is what I'll call unbiased. And by this, I'm just going to define this term. It means exactly what I said, like exactly equal number of zeros and ones. So 2 to the n minus 1 zeros and 2 to the n minus 1 ones. And actually, this happens to be an example of a truth table with that property. This majority happens to have exactly 4 zeros and 4 ones. It happens to be an unbiased function. Okay, so that's kind of nice because it is some understandable, like human understandable property of f. It's like, oh, the amplitude on all zeros, one thing we can say is it eventually gets to be 0 if and only if f is unbiased. And that's maybe an example of like some secret or mystery about f that maybe you didn't know before and you might kind of be interested in. I mean, I don't know if you'd have like if I give you some Python code that takes as input n bits and it returns 1 bit, and I ask you, hey, is it true that like for exactly half of all possible inputs, this function returns true? It's like a mildly interesting question that maybe you'd be curious about. And evidently, somehow, the amplitude on the all zeros string tells us something about that, the answer to that question. So, just to continue this, conversely, I mean, if f's truth table is is biased, by which I literally mean not unbiased, so it has a different number of zeros and ones, then the final amplitude on the all zeros basic state is not 0, non-zero. Okay, it could be positive, it could be negative, it's not 0 though. Okay, that's the only conclusion I'll draw. Okay, so I'm building up here to like some kind of quantum algorithm that somehow tries to detect if a Boolean function has an unbiased truth table or a biased truth table. That's where we're going with this. So I guess as a consequence, suppose at the end of this paradigm, you did the extract all. Okay, what would happen? Well, normally when you're about to do extract all, you're like, okay, let me first clean up and make sure my state is normalized. Actually, you don't have to worry about that here for a couple of reasons. First of all, it's going to be normalized because actually we did the same number of add and diffs as we did average and deviation. We did like n add and diffs at the beginning to make the uniform superposition, and then we did like n average and deviations at the end to do this Hadamard transform. So actually those square root halves are going to cancel out and everything will be normalized. Alternatively, you're going to see what we're about to say, we're not going to even exactly compute all the probabilities. We're just going to make some qualitative observation about them. So what I want to say is, if, like kind of case 1, F's truth table is unbiased, then the probability that like the output is all zeros is what? It's 0, yeah. It's 0 squared, which is 0. Okay, because if it's unbiased, then the final amplitude on all zeros is 0. That's something we just noticed. Okay, the final probability of outputting all zeros is the square of the amplitude on this. So it's the square of 0, which is 0. Okay. Frankly, we don't know anything about like what is the probability of outputting any other string, because to figure that out, we need to know the amplitudes on all the other bit strings, and we didn't figure that out. But we can at least say the probability of outputting the all zero string is 0. So if it's unbiased, this whole routine will never print out all zeros. On the other hand, suppose F's truth table is biased. Well, the probability of outputting all zeros, well, here we don't exactly know either, per se. We just know that the amplitude on all zeros is not 0. But there's a funny thing. It's like some non-zero number squared. So when you square a non-zero number, you get a non-zero number. So you get something that's not 0. And let me additionally say, you get like a positive number. Like you get a probability which is not 0, so you can say it's greater than 0. Okay, so let me now, because things got a little bit scattered, let me summarize like everything we have shown. We've actually kind of constructed a quantum algorithm that does something. So let's summarize what we've got. This is what I call the quantum bias busting algorithm. The real name of this algorithm is Deutsch Jozsa algorithm, after two people called Deutsch and Jozsa, who discovered it around 1992. So I'll summarize everything we've done. So let's say you're given as input, this is kind of funny, but you're given as input some classical and or not code. Or you could really have Python code and you convert it to and or not code, but let's just say and or not code, computing some Boolean function with n inputs and 1 output bit. Okay, somebody gives you this long 5,000 line and or not code instructions, kind of the sort that like went into the programming exercise about probabilistic computer simulator, except maybe, well, that had like C-naughts and stuff. Anyway, you get some like 10,000 lines of and or not code operating on some n equals 1,000 bits. And you kind of imagine you want to know, hey, is the complicated function computed by this code, does its truth table have the property of being biased or unbiased? imagine you wanted to know that. It's not totally ridiculous. Okay, so step one is you do everything from last lecture. You convert this like and or not code to quantum code for the like if f then minus instruction. Okay. And now you start doing some quantum code. You do new qubit B1 through Bn. And then you do, I mean, really, you do Hadamard all, but we're going to say, this one we're going to call add and diff all. Okay, and the point of that is now we have the uniform superposition on all 2 to the n basic states. Okay, now we do if f then minus, which we built the code for. If f on like B1 through Bn, then minus. And now we have this like glorious state where like all the 2 to the n plus or minus 1s of f's truth table are in the state. Now we do like the Hadamard transform. So like formally we do Hadamard all, but for bookkeeping purposes, we now think of it as average and deviation all. Okay, that's the Hadamard transform. Now we know something about the amplitude on the all zeros string. It's like the average of these truth table values. Then we do extract all. And now let me add like one line of classical code. This one last line of classical code is if the display of extract all is like all zeros, then output like print on the screen like biased. Wait, yeah, biased. Else output no comment. Okay, so like this is something that you could do if you had a quantum computer. You could build this routine that took in some and or not code for computing a Boolean function, did all this stuff, and that code will eventually print out either biased or it'll print out I have no comment. So let's think about what this algorithm does, what it accomplishes. So I'm going to list out here 3 or 4 properties that this basically quantum algorithm has. Okay, so properties. And as I said, this code is like trying to like, you know, bust f if it's computing a biased function. Okay, it's trying to be like, ahaha, this input you gave me has a biased truth table. Again, it's kind of a weird thing to care about, but let's imagine that you cared about it. Okay, so one, this algorithm has no false positives. Okay, in other words, if it outputs biased, then f's truth table really is biased. Okay, so why is that true? Well, what I want to say is like, if it outputs bias, then it can never be that f's truth table is literally unbiased. Because if f's truth table is literally unbiased, then we know the probability that the extract all gives us zeros is literally 0. And therefore, if it were unbiased, we would never, ever, ever get all zeros here, so we would never output biased. Okay, so this code will never give like, you know, when it says biased, that's you have an ironclad guarantee that f truly is biased. Okay, that's good. So far, that's not impressive because, like, here's another algorithm that also has no false positives, and it runs in one step. The algorithm is always output no comment. That has no false positives. You're like, yeah, but that's also, like, it has no power at all. It sucks. Another property this code has is this algorithm has at least some positive power. This power is, I guess, like a technical term from statistics but let me just say what it means. If F's truth table is biased, there's at least some positive chance that you catch it, that you bust it. Probability, the algorithm busts it, output's biased. Okay, and why is that true? Well, again, as we saw, let's say you give it some f where the truth table is biased. Then the probability of outputting all zeros is not 0. It's strictly positive. It's definitely positive. And therefore, this code has some positive chance that it displays all zeros and therefore outputs biased. Okay, so the algorithm is sort of non-trivial in this sense. Okay, the third property I want to mention is that this quantum algorithm is efficient. Again, I'm not going to like really get into like big O, running time, and so forth, but let me just say that what is the total number of operations? The total number of operations is, well, I'll get a little bit into big O. It's big O of n because, well, I don't know, you have to like make n qubits. That's like n things, and you have to do add and diff all. This is like n operations, and you have to do average and deviation all. It's like n operations. You have to look at the n output bits. That's n operations. But okay, it's order n plus. The other main thing you do is this one, if f then minus. And we saw that like the number of quantum instructions you need for this is roughly comparable to the number of classical instructions you had for computing f. So like if this is L lines of and or not code, this is something like 2L lines of quantum code. So this is plus order, like the number of lines of and or not code. And probably this one's bigger than this one because, like, I mean, this and or not code probably like looks at all the input bits, which is already n of them. So basically, this is efficient in the sense that, like, okay, if there's like 10,000 instructions here, then the number of quantum operations you do is, I don't know, 20,000 or something. Okay, so these are the four main properties, or the three main properties of this quantum bias busting algorithm. There is a fourth property, which is that this algorithm is practically utterly useless. It's practically useless. So I'll put a little ironic happy face here.